Okay, welcome to another edition of organic chemistry lecture. We're going to try to do this in just one meeting, unless I get too many participants. In the meantime, shoot for one. So we'll start where we left off. Where we left off last. We left off last and talking about how we make aldehydes. We talked about that. Oh, okay, we can oxidize alcohols, and we can use Grignard and other methods to add nucleophiles like hydride and R- to nitriles, and then exchange the nitrogen for an oxygen, making aldehydes and ketones. So, continuing with that thought, we can also make aldehydes from acid chlorides and from esters. So acids we have some sort of acid. We have acid chlorides, and our esters. So now the problem is here with some of these guys, if I just try to add lithium aluminum hydride, yes, they will end up going to aldehydes. They'll go to what? Oh, we'll go to that. But unfortunately, this is very reactive, and we'll keep reacting until we get to a primary alcohol. So we need to turn acids into something that's much more reactive than the aldehydes. And so that's where we can bring in the acid chlorides. Acid chlorides do not need nearly as strong of a oxidant. We don't need lithium aluminum hydride. We can use something much weaker to do that. So the first thing is, how do we make acid chlorides? Acid chlorides can be easily made by using our dear friend, the thionyl chloride. So we can use from this. This is going to be a big part of making acid chlorides later when we get to the end of the semester. But you're going to use this compound, OCl. This is particularly reactive because it will give a Cl, it will fully oxidize to SO2 and form HCl gas. And as we drive these two things off, it's not going to be reversible. So we're going to drive off HCl gas, SO2 gas, and we're going to be left with what? RCl. Acid chlorides are not particularly stable, which is why they would be very useful. We can add in a weaker source of hydride transfer. So instead of lithium aluminum hydride, which has 4 hydrides it can kick off, we can use this, which we maybe discussed in the past. Lithium aluminum, there's a hydride, but the other 3 places have a butoxide. So there are going to be negative sources that are going to be donating into the aluminum, but they're also going to be steric bulk. So we're going to only have one hydride that can transfer. With lithium aluminum hydride, we could transfer multiple hydrogens or hydrides, and that yields the fully reduced to the alcohol. So if we do this with some sort of acid chloride with our weaker reductant, aluminum, it's just going to result in our aldehyde. And we're going to kick off the hydrogen, the chloride. Now, we can do the same thing with, or at least a very similar thing with esters. Slightly different compound, but with esters, we can add our diisobutyl aluminum hydride and a really cold temperature. So we use our diisobutyl aluminum hydride at -78, we can you essentially form the RCHO, which is bound to the aluminum. And then in the presence of then the water, you essentially, the water is going to pronate this, and that's going to leave as an alcohol, and that's going to shift back down. Tap the water, leave, and that's going to shift. And then we have our aldehyde, our alcohol product. Move my face out of the way. So essentially we have what we want to do is we either have to use a less reactive reductant with a more reactive compound. And we can force this to an aldehyde and stop there. We could also do similar thing with acid chlorides using Grignard or organolithium, but unfortunately they end up being too reactive. So if I add acid chloride with Grignard, say, let's say methyl lithium, it's first going to go to, oh, hey, we're going to go to methyl, but it's going to keep adding. It's going to keep adding, and then you're like, oh, crap. So we have to find a way, we'll have to find a way to add just one. And we've done this. We did talk about this. We talked about this earlier. We use lithium dialkyl cuprates, where we, instead of using methyl lithium or something like that, we would mix our methyl lithium or whatever our group is with copper chloride, or copper iodide, sorry. Copper iodide, two equivalents of that. And what did we form? We form this this dialkyl copper lithium with a lithium iodide, which is just a salt that can be removed. So this dialkyl copper lithium complex can then add just to replace that chloride. So we're once again, what's the idea? Aldehydes are a particularly reactive intermediate. So we have to use a alternative method to transfer and stop at the aldehyde. You can either go all the way one way or all the way the other way. So that's what we got to think about. What do we have? How reactive is this guy? So we can just add the R group. So add the R group and give us our ketone. You get essentially a methyl copper and a lithium iodide or lithium chloride. That's the byproducts that will be removed. But so far the premise right here is that if we want to stop at an intermediate, we need to find a way to add with a weaker source, something that's not going to over add, something that's going to just add one equivalent, something that's only going to add to one spot. It's not going to add to everything. That's the problem with Grignard. Grignard and organolithium are particularly reactive intermediates. They're particularly reactive, reagents. And so long as you use them, you're going to add to a bunch of different sites. You're going to add to any acidic site. You're add to any carbonyl site, any amine site, any nitrile site, any sort of polar organic double bond kind of thing. So that's why you have to protect this site, or you have to do this and do that. So if you find a weaker way to add, sometimes you can use that to add and stop at the middle portion, which is what we have to do. But all those are just ways in which we can make some ketones and aldehydes. Now, what reactions can we do with these guys? Well, we've already covered a lot of these guys. And a lot of them we're going to follow some sort of nucleophilic addition type thing. We're going to have a nucleophilic addition where we add a nucleophile to the carbon of the carbonyl, followed by electrophilic addition of a hydrogen across the carbonyl to form the to pronate the oxygen. So we've seen a lot of these already, but we'll just go through them because we always got to remind ourselves, what do we know? We've learned about Grignards. Grignards going to add to this. We say, oh, if I have some sort of ketone and I add a Grignard or organolithium, step one, we use our solvent of ether. Why ether? Ether is not acidic. If it's not acidic, then we don't have to worry about the Grignard being used up by our solvent. Step two, we're going to neutralize the Grignard and neutralize our acid. So we're going to add our R group, nucleophilic addition, and then pronate the hydroxide with the electrophile. We've also done this with our hydride adders, sodium borohydride. We can add those. Said lithium aluminum hydride. All these guys, if you do this with, say, methanol or whatever as a solvent, some sort of solvent that can donate a proton. We don't even need a full proton. Methanol, ethanol, some solvent. We're going to just get, in this case, instead of a tertiary alcohol, we're going to get a primary alcohol. A secondary alcohol. So, let's say in the case of, we can do this sometimes backwards. We can do it electrophilic addition as well. These guys can do that because oxygen is particularly reactive with its two lone pairs, and it's very polar. If I have acid pair can attack there. Or actually, sorry. Step. So reacts, and you would have the carbon, the oxygen has a positive charge. Water. Attack there. And then depronate. You can form a diol, geminal diol. I know I skipped the step of the depronating the water again to reform our catalyst, but go through that. Now, when we deal with these, aldehydes are generally more reactive to nucleophilic addition than ketones due to the electron effects and the steric effects. Essentially, that the hydrogen has less electronegativity. I mean, essentially the electron, has a less electronegativity. It cannot be donating any electron density into the carbon. The carbon is more weak to has a greater positive charge comparing to this. So inductively, the carbons are putting electron density into that center carbon as the electron density is pulled up. Now, an aldehyde only really has one big source of electron density, and that's that methyl. The hydrogen cannot be putting too much electron density into there. There's not much to put into it. So that carbon is more positive than, say, that carbon. And also that hydrogen doesn't take up much room. So that hydrogen does not provide any steric hindrance to any nucleophilic attack. So with that in mind, aldehydes will typically undergo the nucleophilic addition first rather than electrophilic addition. But most of these reactions are reversible. They're all reversible. Is just where does the equilibrium lie? But we could look at acidic mechanisms and basic mechanisms, and they're both get up the same effect. Just one might be favored, say, with aldehyde versus ketone. So, let's look at the basic mechanism first. The nucleophile. We have our ketone. Base attacks. Form our the oxygen oxide, and then that oxide can then depronate a pronated nucleophile, and thus forming this compound, OH. Now we can do the same thing if we do it an acid. So if we say, for example, we have a particularly weak nucleophile. You could go the opposite way, which we just kind of showed this one. The diol, H nuc, tack that, form our H plus, and then now a nucleophile can then attack the back. Because this guy has the resonance structure. This has the resonance structure of that versus that. We can put the positive charge of the oxygen or the positive charge on the carbon. And this guy really gonna attack that carbon, form that same byproduct over here. Same byproduct. So we just kind of talked about this one, but so one of the major reactions here is the hydration of a ketone. You add water and you're going to form the diol. Now this could either be acid or base catalyzed. But generally speaking, this guy is mostly reactant favored. There's a K expression with the hydrate on one side and hydrate on one side and the ketone and water on the other side. So the K is going to be hydrate over ketone. And because water is no longer solvent usually, water can play a part. This the ketone is usually more stable. It's more stable than aldehyde and way more stable than formaldehyde. So like if you look at this KEQ, most ketones have a KEQ. So you got to remember, what does the equilibrium constant mean? The KEQ is somewhere between 10 to the negative fourth to 10 to the negative second. If you look at an acetone, KEQ is approximately 1. So you're kind of flipping back and forth between the diol and the aldehyde. And the formaldehyde, which is the methanal, actually prefers the diol. It's actually, the KEQ is actually something close to 40. So it's really actually, the diol is probably more favored than formaldehyde. Now, so you can also stabilize these guys by putting electron withdrawing groups onto the ketone. Will stabilize the hydrate because you have a large amount of electron density on here. So if you can pull the electron density out of these oxygens, you can make this more stable. So some other things you can form from ketones. Cyanohydrins. So let's break that down. Cyanohydrin. Cyano is cyanide or Cn minus, and hydrin, your water. So it works under the same premise. You mix in HCN and then either KCN or NaCN. So like essentially a cyanide buffer. That Cn minus is a strong nucleophile, and HCN can protonate this. And essentially what you can form is cyanohydrin. Now, towards this formation, formaldehydes, once again, they're going to be more reactive than aldehydes, and aldehydes are going to be more reactive than ketones. Now, while some ketones will react relatively well to these, bulky ketones will not. You got to think about it. You have to be able to, the same thing with nucleophilic addition. This is like a SN2 reaction, meaning that back attack. This is not necessarily going through the carbocation intermediate. So we need cyanide to somehow fit into there. So if these are, say, phenyl groups, it's going to be a little bit harder, or tert-butyl groups, it's going to be a little bit harder for that cyanide to attack in that little pocket and thus kick it up. Now there's an alternative thing is that we could condition is we can use the cyanide first and then use a protic solvent to protonate the oxygen later, but that's not a big deal. Let's say, okay, another thing we can do is well, that the one reason why is this weird compound? Why is a cyanohydrin important? Why is a cyanohydride important? Is because that nitrile, remember that imine, when we talked about imines can be exchanged for ketones by using oxygen, by using acid. Well, cyanide can be hydrolyzed to carboxylic acids. So for every bond to carbon, you can add an oxygen bond to that carbon. So when you have a carbon-nitrogen double bond, you can add a carbon-oxygen double bond. But for a carbon-nitrogen triple bond, we can add 3 carbon-oxygen bonds. So why is this important? Well, I could protonate this and form a carboxylic acid. And so those cyanide, so well, H3 double bonds. Well, 3 carbon-oxygen bonds. And so that's why cyanohydrins are actually semi-useful for us in terms of complexes. So then we have imines. We can form just the same way we could turn imines into ketones, we can turn ketones into imines. A substituted imine is an example of a Schiff base. So imines form from condensation. They're gonna so what we're gonna do, take a ketone, for example, and we're gonna add an amine. And in the presence of acid, we're going to form this compound. So this intermediate. So we form this. This is a hemiaminal. Hemiaminal. So I think sorry. Yeah, I definitely screwed that up. Okay. Hemiaminal, which will then switch to an imine with a transfer of another hydrogen, switch to an imine, whatever saying. And or water. The idea is well, in the presence of acid and an excess of water, it's going to push this out and reform a ketone. In the presence of an excess of amine, it's going to push the ketone out and produce small amounts of water. So we're going to force this to the amine. Now, we can also, let's see, this forms essentially the mechanism over here is actually a acid catalyzed dehydration. Essentially what's happening. So the actual mechanism, we're going to say, bring in here, lone pair first attacks the proton, form R H plus. Oh, for God's sake. That intermediate, which can exchange for this intermediate. This intermediate can then be attacked by our nitrogen. To form the protonated carbonyl. So we have the H N R H H, and that's positive. Then our solvent or whatever, however we added the proton, this can reform. Sorry, arrow going the wrong way. Just going to go back to there, and we're going to kick off our proton. And that what does that do? That essentially reforms it's going to reform our catalyst, our proton. Minus a proton. That gets to our carbonyl. Then from there, we do it again. This R with its lone pairs, another proton to give us our intermediate, to give us our hydrated water leaving group that can now go away. So that gives us our intermediate, which is is we can go, oh, either this is positive there, or the lone pair has formed our double bond and the nitrogen is positive. Once again, from that positive nitrogen, we can be depronated again, and we form our imine. So essentially, we have electrophilic addition to the alcohol, nucleophilic addition to the carbocation, then depronation of the ammonia to reform our catalyst. Then we do it again. Electrophilic addition, followed by the lone pair. We form the double bond and depronation. So just make amine. This needs to be mildly acidic, but not too acidic. So if it's too acidic, we won't keep the amine around. We'll just completely pronate that amine. So, and amines can be hydrolyzed back off again with acid and excess water. So the key thing is not too much water, not too strong of acid. And we can do that, but that's just one of the things we can do. Let's see. We can also make hydroxylamine in hydrazines. So a hydroxylamine, we can add hydroxylamine and hydrazines. Hydroxylamine is, an amine, remember, is NH2. So hydroxylamine is NH2OH, and hydrazine is a diamine, NH2NH2. Those are kind of weird, but the same general idea. When we add a NH2R to form a substituted amine, the same premise. In the presence of acid, a hydroxylamine will form what's called an oxime. An oxime being a amine substituted with a alcohol. I know, that's weird. Weird. We have hydrazines. So, same general premise. In the presence of acid, a hydrazine will do the exact same thing, form what's called a hydrazone. And you can also do all sorts of weird stuff, but the same general premise here. A semicarbazide. My God, this thing's a hot mess. These are some things that I assume are going on in your body, in nature. But do this. And what's that going to form? A semicarbazone. So N and H. So, but the same general premise is that NH2 is adding and replacing that oxygen as water. Adding and replacing that oxygen as water. Now, for those who are going to go into biochemistry, the next one will be, let's see how far we get, but we're going to talk about acetals very briefly. Acetal formation is, so instead of doing this with amine, we're doing it with alcohols. We're going to add alcohol to these guys, acetals and hemiacetals. So to this group, we're going to add 2 equivalents of ROH. in the presence of acid. The same general premise here being we're going to form, you're going to protonate this, you're going to add the OR. And now if you allow this to keep protonating it, you're going to have either a ketal or a acetal. Plus water, because you're essentially pushing, if you have an excess of ROH, you're pushing the equilibrium to the right. You're pushing the equilibrium to the right. Yes, you could probably get it to just add once and forming a hemiacetal, which is the mixture of alcohol and ether. But if you have an excess of alcohol, you can push it to the right to form this ketal or acetal. Technically, they're both acetals, but you could specifically say that's a ketal. But this must be acid catalyzed. This cannot be base catalyzed. Now, the intermediate, as I said, is the hemiacetal. So let's look at this. Let's look at the mechanism here. If I did, so let's start the first thing. I'm going to skip the lone pairs because it's hard enough to draw the dots. So we're going to form our intermediate transition state, OH plus, between that and OH. Now, the ROH, oxygen's going to go there, and then that forms our, almost at it, but we're at the intermediate, which is the, yeah, this is being plus, and that's going to be, oh, the electrons go there and we lose the acid. So that forms our hemiacetal. That's our middle point. Our middle point. Now, from that point, here's the ingenious part. The acid could add, well, sorry, the other way around. The acid could add to the alcohol, or it could add to the ether. If it adds to the ether, well, you just kick that back off, and then you reform your ketone. You kick it back off and you reform your ketone, and that ends us back at starting materials. But if you allow it to add to the hydroxyl group, that forms our stable. We formed, oh, there's OH2, that plus, so that's going to off. And then we have our transition state again. So we have our, oh no, we're carbocation, which can transition between that and positive is on the oxygen. And from there, we see our R prime OH adding again. And finally, erase some of this. Just so I can keep this. Find the last step. We have our OR prime that there's positive charge here. We depronate this to form our acetal. Now, thing I want to leave you with before I go, the thought I want to leave you with before I go is that if we do this via base catalyzed, we're going to get stuck right here at the intermediate. The base catalyzed, I can add that hydroxo here and then pronate it, but I'm going to be stuck with a hemiacetal. I'm not going to be able to kick this guy off. And so I'm stuck at the hemiacetal if I do base catalyzed. Maybe I can add and get to the hemiacetal, but I won't be able to get to the acetal if I use base. So I have to use acid in order to be able to kick off that water, that ketone is water. Now, this process is very reversible. So all these steps are reversible. So excess alcohol, usually using as a solvent, will favor the formation of acetals. If I use acid and water as the solvent, it will reverse very easily back to the ketone. So we have to choose our solvent wisely. Now, why is this important? Well, there are certain protections we can do, but also you got to think about when you think about your sugars, all your sugars, which is your like 6 carbon, 5 carbon, like pentanol, like multiple alcohol groups with a ketone at the end. When it cyclizes into that 6-membered glucose or lactose or whatever you're making, you're forming an acetal linkage, well, your hemiacetal linkage. And then when you form that glycosidic bond, when you link 2 sugars together to a disaccharide, you're forming an acetal. These are hemiacetals and acetals are present in all of our carbohydrates. Just something to keep in mind. We're going to continue from there on Friday. Thank you for watching. Good day. Word up.